It's the 4th of June 1996, and the European Space Agency is launching its brand new Ariane 5 rocket for the first time. This is a big deal. The Ariane 5 is designed to carry large, expensive scientific and commercial payloads into space and heralds a brand new era for the ESA. A decade of design and testing and billions of euros have led up to this day. The Ariane 5 rocket carries no astronauts. The first payload is 4 very expensive scientific satellites to be delivered into orbit. Things start well, the rocket clears the tower and accelerates smoothly, and then the rocket abruptly changes direction, starts to break apart, and suddenly explodes. Less than a minute after launch, huge chunks and glowing fragments of Ariane Flight 501 rain down over the launch area. A shocking disaster for Ariane and the ESA. The cause? A simple, utterly avoidable coding bug. Okay, here's what happened. The Ariane 5 leaves the launch pad and accelerates smoothly into the sky following its predetermined path towards space. Inside, the onboard guidance system is constantly tracking the rocket's trajectory and sending the data over to the main flight computer. To do so, the guidance system converts the velocity readings from 64-bit floating point to 16-bit integer. Okay, stop for a second and let's think about what that actually means. Computers store numbers in a variety of ways. Consider 4-bit integers. 4 bits can represent anything from 0 to 15. But if you want to represent the number 16, well, there just aren't enough bits, are there? 16's too big. You need more bits to store bigger integers. With 16 bits, you can store anything from 0 to 65,535. Or, if you throw in a sign, then 16-bit signed integers cover everything from minus 32,768 to positive 32,767. But anything bigger than that, and again, you've run out of bits. Floating point numbers are stored a bit differently. They're stored as a decimal, or significand, and an exponent. The details aren't really important here. All you need to know is that 64-bit floating point can store much larger numbers than can fit into a 16-bit integer. So converting between them can be tricky when the integer runs out of bits. So what does happen when you run out of bits? Well, if you're using 16-bit signed integers, the conversion will just wrap around to the beginning again. But whatever the details, you're definitely getting the wrong answer. And this is known as an integer overflow. Right, so back to our rocket. The guidance system reads the horizontal velocity data of the rocket as 64-bit floating point and tries to convert that into a 16-bit integer to send over to the main flight computer. But at that moment, the velocity reading is actually larger than the largest possible 16-bit integer. The system tries to do the conversion and fails. Now, a clever system would have some procedure built in that says, hang on, we're piloting a rocket here. I need to say something sensible to the main computer. It would have some overflow error handling code. But in this case, the guidance system code isn't very clever. So it just sends an error message in place of the velocity data and promptly shuts down. Fortunately, there's a backup guidance system in case the primary module breaks down. Unfortunately, it's running the same code, so it does the same conversion, gets the same overflow, and crashes for the same reason. The main computer receives the error message, and because there's no handling code built in, the computer interprets the message as real navigational data and immediately freaks out. The velocity reading is off the charts, indicating that the rocket is dangerously, impossibly off course. So the flight computer does what it's designed to do. It fires up the boosters and drags the rocket around in an attempt to rescue itself from a non-existent disaster. This puts the fuselage under incredible aerodynamic strain, which starts tearing the rocket apart. Detecting that things are now really going badly, the computer calls it a day and triggers the built-in self-destruct mechanism. So, what was the ultimate cause of this incredibly expensive, very short, and ultimately catastrophic rocket flight? A simple line of code, converting a floating point to an integer that led to an overflow, passed without warning to the main computer, which was interpreted as real, if wildly inaccurate, data. The flight software had been used previously with no problems on many flights of the smaller Ariane 4 rockets, But the Ariane 5 was designed to fly faster than anyone planned for when the software was originally written, and the higher velocity led to the overflow error, a flaw that should have been found, it just never came up. Want to know the worst bit? That buggy bit of code wasn't even necessary during flight. It was part of the launch pad alignment process and shouldn't have been running after liftoff. But sometimes, a small glitch somewhere causes a launch to be delayed by a few seconds. So to save having to reset the system, the original programmers decided to keep that bit of code running for 40 seconds after the scheduled liftoff time.